Hi, welcome to this lecture 6 on week 7 of the course on linear systems theory. So, this lecture we will discuss some important aspects of what if the system is not controllable and how to even identify post the controllability rank conditions of what are the possible modes that are uncontrollable. So, we will use the property of invariance with respect to similarity transformations. Okay, so we will be as usual interested in both continuous and discrete time systems, and what we saw in earlier lectures is that if there is a similarity transformation z equal to t inverse x, which takes the system to from x coordinates to the z coordinates, I have a new system z dot is a z plus b u with a new a and a b which look like this. Okay, so the first thing that we will look at it is okay, assume that the pair AB is controllable. What happens to the pair A bar B bar? So, a quick result says that this pair is controllable, or when I say the pair AB is controllable, I am essentially looking at controllability of this system. Okay. So, when this system is controllable, then so controllability of this system automatically implies controllability of the transformed system. Okay, so it's a very quick proof. Let's just write down the steps. So what do I have? That if I have x dot is a x plus b u, the controllability matrix looks like this. So we have b a b all the way till a n minus 1 b. Okay, now I have z dot is a bar z plus b bar u. Okay. So, what is the controllability matrix here? This will look like b bar, a bar, b bar, so on until a bar n minus 1 b. Okay. Now, what is a bar? That is t inverse a t. B bar is T inverse B. Okay, I just substitute those here. So, what is B bar? B bar is T inverse B. What is A bar B bar? A bar B bar is T inverse A T T inverse B, right, and so on. So, if I just write this down, what I will get here is I just take this T inverse out. I have B. This will be the identity. I have AB. Similarly, I will have A square B as the next term till A n minus 1 B. Okay. Now, okay, let me call this C bar. Now, what is the relation between rank of C and rank of C bar? Okay, because this is an invertible matrix. That was the condition for the similarity transformation. What we get is rank of C is rank of C bar, and therefore, if this system is controllable, the transform system is also controllable and vice versa, right. So, that is the proof of this, that the pair AB is controllable if and only if the pair A bar B bar, which comes as a result of this similarity transformation, is also controllable. Okay. Now, now this is important. We will look at what if the rank of the controllability matrix is some q which is less than n. Okay. So, the controllability matrix B to A n minus 1 B, ideally you would assume that they would have n independent columns, right, for them to be of rank n. Now, if the it is not full rank, then it will be of some rank which is q, and that is less than n, right, at least. So, which means that there at least be q linearly independent vectors here. Okay. Now, this C will be A invariant. Okay. Now, again, so I will just recap what we did here, right. So, I was in this lecture from week 3, we had what we had what we called as an invariant subspace. So, if we had a linear transformation represented by the matrix A S, which was an m dimensional subspace of R n. So, here if I look at I have some kind of a q dimensional subspace of the controllability matrix. Okay. So, now this S is A invariant, which means I take any element x from S, I multiply it by A and I get S, right. So, A times x is again in S, which means that S is A invariant. Okay. Now, V1 till Vm were the basis for these subspaces, okay. And then so I just call them this m vectors. Okay. Now, I know that A times Vi is in S because of invariance, okay. And this A Vi can be written as a linear combination of basis vectors of F, and therefore, I can have an expression like this, right, that A times V is V times A bar, where A bar is a m cross m matrix. Okay. So, this is what we did earlier too. Okay. Now, in that case I take this m independent vectors which come from here, m independent vectors which come from this subspace. I can always add to it n minus m vectors such that this T is a invertible matrix, or such that this U together with this V forms a basis for Rn. In that case, my T inverse At, where T is constructed from here, takes this form. So, it has a nice decomposition here, right. I can just split it very nicely in this way. Now, let us see what this means in the case of controllability or the cases where I actually lose controllability. Okay. So, I have this q independent columns. Now, to this q independent columns I add, so V1 till Vq, I can add some Vq plus 1 till Vn such that this will form the basis for Rn. Okay. And then do the similarity transformation. Okay. So, now this T inverse At will look something like this, exactly similar to what we were doing here, and now it will be kind of obvious of why this particular concept was taught earlier in week 3. Okay. So, what happens to B now? Okay. Now, since the image of B is a subspace of C, the columns can be written as now independent as linear combination of the columns of V. That is, there will exist a Q cross M matrix again in the similar way, B with a suffix C such that B equal to T times BC, or T inverse B is BC, and then you have a set of zeros here. Okay. And this will be a Q cross M matrix, right. Okay. Now, for every LTI system, this is what we also proved earlier, there is a similarity transformation that takes the system which is of this form. T inverse At looks something like this, T inverse B looks something like this, and in the transformed system, the controllable subspace is also transformed as this one. So, only the Q modes are controllable, right. So, here the rank of C was equal to Q, and therefore, C is now just the image of that Q cross Q subspace, and in this case the pair AC and BC will be controllable, right, and this is of AC is from R Q cross Q, and the rank of this matrix BC till A n minus 1 BC is Q. Okay. Now, this pair is controllable, not A comma B is not controllable, whereas some smaller A AC and some smaller B is controllable, which means there is at least one smaller part of the system that is controllable. Okay. So, what happens to transfer function, right. So, it is easier or it's useful now to look back at control 1 and say, oh, well, there is something which is going wrong here, that the system is not controllable. Let us check how the transfer function looks like. Okay, so I have a decomposition here, z dot, okay, is also could do the same thing in discrete time. I have AC, BC, and so this is with the decomposition that we did earlier. C will have some terms like this, okay, whatever they could be. Now, if I write down the transfer function, okay, how do I do the transfer function? I just do C S I minus A inverse B plus D. So, I do all those steps, should be very easy to check, and I just end up with the transfer function just having terms related to AC, CC, BC, and of course D. So, this is a little important to note here, right, that the transfer function, and what is this AC and BC? This is the controllable part, right. So, this pair AC comma BC was controllable, and therefore, I can conclude that the transfer function is the transfer function of only the controllable part. What happens to the uncontrollable part? Well, that just disappears in those as a result of certain pole 0 cancellations. Okay. So, sometimes when I give you a transfer function, that may not really be a completely controllable system, right. And if you look at also it in terms of, so this is of dimension k and of dimension n minus k. So, this the last n minus k x dot of n minus k is just AU, it has no control entering here, right. So, this AU times, okay, x n minus k, okay, there is no influence of the control input to this n minus k states, right. So, that is why we actually can nicely separate out the controllable part and the uncontrollable. Therefore, we call this the AC and this we call this the AU, denoting the uncontrollable part, right. So, the BC, the control input affects only the first, sorry, it should be Q, right, that is what we assumed, a Q here and a n minus Q, right. So, Q is controllable and the remaining n minus Q are not controllable, right. Okay. So, we go back to this example of the parallel RLC circuit. So, we concluded, or we could easily derive that when the time constants were equal, the dimension of the subspace is just 1, or the system is not controllable, the rank of C is 1. Okay. Now, if I just look at the controllability matrix, okay, there is a linear dependence here also, therefore, I can say that rank of C equal to 1. If I just choose a basis 1 1, right. So, this vector together with a vector which is linearly independent of 1, just say 1 minus 1 transpose, you could also look at 0 1 transpose, 1 0 transpose, and so on. Okay. So, I construct this transformation T from V which comes from the number of independent columns of the controllability matrix, which is 1 in this case, and U, which is an additional vector we construct in such a way that this U plus V together span R2, right. Okay. Now, I do all the transformations, T inverse AT will look something like this, T inverse B will be of this form. Okay. So, I have a system which now looks like this. So, if I look at here, see the Z2 term does not have any control influence, it is only the Z1 that is getting affected by the control input. So, you would expect the transfer function to have 2 poles, but then if I just compute the transfer function from the from this formula, I just get that it just has 1 poles, sorry, just 1 pole. Alternatively, what you could also do is compute the transfer function of this system assuming a certain output, and then when you plug in this equality there, that the time constants are the same, then you will essentially see a pole 0 cancellation. Okay. So, in this case also I am dealing with a system which has 2 states or essentially 2 poles, but then because of the dependence of time constants on each other, or the time constants are equal, there is a pole 0 cancellation, and you just look at it as a first order system. Okay. And this is something which we miss while we do the transfer function based analysis. We assume that everything is nice, that there is no pole 0 cancellation and so on. Okay. So, now just look at just to conclude, so if I have these modes x dot n minus q is a u times x n minus q. Okay, what do I do with this system? If I say, well, I can only control the first q modes, what happens to these guys? Or okay, this should be written in z coordinates, right, not in x, but okay, it does not matter, it is just a matter of notation. So, if this A is such that the eigenvalues of this are unstable, then the overall system is also unstable. But there is some hope when when these eigenvalues are stable, that this that the remaining n minus q states asymptotically go to 0, then I can do something with the controllability properties of the pair AC and BC. So, that is what we will look at when in the next lecture, where we talk of a weaker form of controllability, which is essentially to do with stabilizability, right. So, we will focus on this controllable decomposition, what to do with the uncontrollable modes and what to do with the controllable modes. Thanks.